Hello Internet, my name is Quinn and this is Blondihacks. Today I'm going to do a beginner's tutorial for silver soldering. If you've never done this before and you're intimidated by the process, or maybe you've done it a few times and you want to improve your results, then this video should help. I'm going to be covering primarily model engineering related topics, but this will also apply to, for example, making your own brazed carbide tooling. So let's go. Silver soldering is a chemical bond between metals. Unlike, say, welding, where you're actually melting the two pieces, fusing them into one continuous piece of metal, this is a chemical bond. Now, that may seem like it's thus going to be weaker than welding, but that's not necessarily the case. For example, when silver soldering two pieces of brass or copper together, the silver solder joint is actually stronger than either of the two constituent parts are. You can fatigue that joint back and forth all you want, and the copper or the brass will fail before the silver solder does. And speaking of which, the advantage of silver soldering over a lot of welding processes is that the joint does remain flexible, which is very important when, for example, making boilers for model engineering. Boilers are essentially copper balloons. They experience a lot of expansion, contraction, and thermal stress during their lives, and a silver soldered joint stays flexible. The other reason to use silver soldering is that you can join dissimilar metals. You can join a piece of carbide to a steel shank for creating a cutting tool. You can join steel to brass, brass to copper, all those sorts of combinations. Everything except aluminum is silver solderable. Step one then is to choose your silver solder. This stuff comes in many flavors. My go-to is Harris Safety Silv 56. That means it's 56% silver, and that's not a metaphor. It is literally 56% silver, which explains how much you will pay for this stuff. It's very stiff, so stiff that it's hard to bend with your fingers. If it's softer than that, then you probably don't have real silver solder. There are a lot of very similar looking products. You'll see things like so-called high silver content plumbing solders that are 5% silver. You'll see Sophos brazing rods, which have silver and a bunch of phosphorus in them. A lot of similar sounding things, but none of those are real silver solder. None of them are safe for steam, and they aren't going to apply to the process that you see here. So if you want a silver solder, especially on boilers, make sure you're using the real deal. Compatibility with steam is important. For example, a lot of the brazing rods used by air conditioning technicians and so on are not compatible with steam. Steam is corrosive. If you don't use the right stuff, you could create a dangerous boiler. Regardless, Safety Silv 56 is really nice to use in any situation. I like it a lot. Another really good option is cadmium-based silver solder, like this stuff here. The Brits would call this Easy Flow 45. The cadmium makes this stuff flow very nicely, hence the name Easy Flow. What that means is it gets into smaller gaps and it makes nice small fillets on your parts, so it makes very attractive looking joints. The downside, though, is right there in the name, cadmium. Cadmium is no joke. They have nasty warnings on this stuff for a reason. Absolutely, you must wear a respirator if you use this stuff and use it in a well-ventilated area. This stuff is probably rightfully so getting more difficult to get in a lot of countries because, let's face it, vaporized heavy metals is not something that most people want to be around. So again, that's why the 56 is my go-to. It's much safer, and it's actually better at gap filling the heavier stuff, so that's kind of an advantage most of the time. I care more about filling gaps a little easier than I care about very delicate little fillets on my joints. The other reason I do keep this stuff around, though, is that it has a lower melting point than the 56. Silver solders come in all different heat ranges, and it's very useful to have multiple heat ranges around in your shop. If you're doing a complex assembly with multiple joints, use a higher heat range on the earlier joints, and then when you do the later joints, you won't risk remelting the earlier ones. That's super useful, for example, in boiler making. The nice thing is there are now lower melting point silver solders, 45% silver solders that don't have cadmium in them. I still have a bunch of the cadmium stuff here, so I'm using it up, but you no longer have to use the cadmium to get the low melting point, which is great for hobbyists. Don't go any lower than 45% though. Silver solder lower than that is not really real silver solder anymore, and it's not going to be strong, flexible, or resistant to steam anymore. You got to have at least 45%. Next, you're going to need flux. Silver solder flux comes in two basic types, white and black. The white stuff is a little bit easier to use, especially as a beginner. You'll find it easier to read. I'll talk about reading the flux in a minute. But the black stuff has boron added to it, which gives it a larger temperature range. And that's important because the game of silver soldering is that you have to get the joint hot enough to melt the solder before the flux spoils. If the flux gets overheated, it stops functioning as flux, it stops cleaning the joint for you, it contaminates the joint, and you'll end up with a bad joint. So for big heavy assemblies like boilers where it takes a long time to get the joint hot enough to melt the solder, the black stuff is great, it gives you that extra safety margin. However, for most basic stuff, the white is easier, and so I use it. This stuff comes in powder or paste form. The paste is a little easier, although regardless of the format, it dries out anyway, so you're going to end up with some version of a powder, and you're going to have to mix it with a little bit of water to reconstitute it. This stuff doesn't go bad, it just dries out, and you can always add water to bring it back. The thickness that you're aiming for is like heavy cream, table cream, or even a little bit thicker. It should easily coat a part when you stick it in there like so. This is even a little on the thin side. Heavier is better than thinner. Now it's time to think about fixturing. Here's 2 freshly machined parts that I'd like to silver solder into a T. So how do I hold the pieces in this position during the soldering? This is very, very important because the parts will absolutely move around while they're being soldered. There's the liquid flux that wants to move everything around. There's the heat and the wind of the torch that's pushing the parts around. You have to fixture things firmly or they will move. Don't tell yourself that you can hold it down with a weight, or that you're going to be careful with the torch, or that you can maybe clamp it. Don't fall for it. The single best method of fixturing is to drill and tap the parts and screw them together with screws made of the same material. And then afterwards you can file the screw heads off, they'll disappear, and you'll never know the parts were ever screwed together. It seems like a lot of effort to edge find and center drill and tap on these components for a joint that only needs to be held together for literally 1 minute. But trust me, it is worth the effort. I have regretted it every time I don't go to the trouble of screwing the parts together. Resist the urge to just clamp the parts together. First of all, you lose all of your joint clearance, which is important. With screws, you can snug them, but don't crank them all the way down. You still get a good silver soldering clearance in between, and the heat is going to ruin whatever clamp you put on there. Now, that said, there are a few other methods that also work. One is tab and slot. If you can create a structure like this coupler pocket here that is completely self-supporting, the parts are all locked together, then that also works. Although even in this case, I screwed the back plate on with some tiny screws, and then this whole assembly was silver soldered and machined down to final shape. Silver soldering an assembly is much like creating your own castings. Beyond fixturing though, joint clearance is extremely, extremely important in silver soldering. You actually want the fit to be a little bit loose between the components. You want between a 1 and 5/1000 gap in there because the silver solder needs a place to flow into. You don't want the joint completely tight, but you definitely don't want it any looser than 6/1000. Silver solder is very, very bad at gap filling. If you get that gap right, the process is really quite easy. Here's a great technique from Kozo for maintaining that gap between 2 pieces that are just sitting together like this. Put some center punches on the mating surfaces, and now that's a little bit of a snug fit. I'll actually need to tap that in, but once I do, those center punches are suspending the part in space so that there's that 1 to 5/1000 gap all the way around the piece in that joint, and that will guarantee that the solder can flow down in there and bond all those surfaces together. Now let's talk pickling. This is a critical part of the process. Silver soldering depends on everything being absolutely perfectly chemically clean. There can be no cheating, no shortcuts on this. You have to pickle and pickle properly. Longtime viewers will know I keep this giant tub of mystery pickling acid under my bench. What's in this tub is Sperex No. 2 pickling compound. This is used by jewelry makers, and it's really, really wonderful stuff. Now, there are other things you can use. 2 traditional options are citric acid or a 10% solution of sulfuric acid. Citric acid is the safest option, but it's very, very slow. Citric acid pickling of a part can take an hour, even 2 hours. Sulfuric acid at 10% is much, much faster. You can pickle something in 5 minutes, but of course, sulfuric acid, kind of dangerous stuff to have around, not great. Sperex No. 2 is wonderful because it's much, much safer than sulfuric acid, but just as fast, 5 minutes to pickle things. You can find this stuff online, Amazon, and so on, but the cheapest place to get it is from jewelry making suppliers. Those are companies that supply people who make jewelry. This 1.1 kilo bag set me back about $10, and it makes 6 liters of acid. and I use 2 of these bags in this tub. So this tub is about 12 liters of pickling acid. I use such a large tub because I'm often making boilers, and I want to be able to dunk all or most of the entire boiler in there for late in the production process. But if you're making smaller parts, of course, you don't need to have such a giant tub. I also keep it in an airtight container to keep it from evaporating. That's helpful with acid solutions because if the water evaporates over time, the acid will slowly become more concentrated, which you don't want. So you want to keep the water from evaporating. It's also useful because as you use this over time, the level in the tub will go down. And that's because every time you take a part out and clean it off, you're losing some of the acid. The acid sticks to the part. So over time, when the level has dropped in the tub, you know that it's not evaporation causing that, so you don't have to worry about adding more of the compound and thus making the concentration too strong. I know if the level is low, I can just top it up with a little more water and a little more acid. I've actually just done that here, and that's why that's a little foamy on top. This stuff gets foamy when you stir it. When you go to stir it, use either a piece of brass bar stock or a piece of wood. Don't use anything ferrous because ferrous materials will contaminate the acid. I also have a little strainer of sorts in here, a plastic that's compatible with this. This is a paint sprayer cup that I punched some holes in, and this is for pickling really small parts like number 0 screws and that kind of thing that would get lost in the giant tub. I also keep a little secondary container of this stuff around for pickling ferrous things, stainless steel parts, that kind of thing. So this stuff will get contaminated over time. It'll turn brown, and then it's no longer usable for anything else. So I don't want to contaminate my main supply. That said, this big tub is basically a lifetime supply. This stuff doesn't go bad, and it keeps functioning essentially forever. In principle, the potency drops as you use it, but in practice, it gets consumed by the process of dipping parts in it long before the potency ever wears off. Back to our parts then, I'm going to put them in the pickling acid for 5 minutes. That's the 2 brass components and the screws. Everything that's part of the joint must be pickled. While that's pickling, let's talk about torches. Most of the time for small and medium-sized assemblies in a hobby shop, your basic hardware store cartridge torch is just fine. You don't even have to buy the fancy yellow ones. The basic propane torches also just fine. These yellow ones, people call them map gas. They are not. Real map gas has not existed since 2010. It was a byproduct of the production of acetylene. This is what they call Map Pro, and it's propane with some propylene added that increases the temperature of it a little bit. So, if you want to feel like a big shot and buy the more expensive yellow ones, like I do, go for it. Makes me feel important. Don't get fixated on the temperature of the flame. Propane is plenty hot enough for all forms of silver solder. What's more important is the size of the flame. The amount or the volume of heat must be matched to the size of your assembly. So for larger, higher mass assemblies, I use this Sievert propane torch. These are technically roofing torches. That's how they're sold. That's their intended purpose, but they work great for silver soldering boilers and other large assemblies. They come with their own regulator that screws onto a standard household barbecue propane tank. Super inexpensive, super handy. You can get all different tips for them. There's a medium-sized one, a big dragon fire breather for making big boilers, and you can also get these little tips for them, but as you can see, I've never used mine because I use the smaller torch rather than using the tip this small. All right, but let's talk about the elephant in the room, oxyacetylene. Why don't I use it? All the cool kids on YouTube use it. It's the hottest torch, and it's also the coolest. You know what I mean. So it must be the best, right? Oxyacetylene is really amazing stuff. It is such a great tool for forging, for fabricating, gas cutting, gas welding, except I think it's not a great choice for silver soldering. You really don't need that peak temperature that acetylene has for silver soldering. And in fact, it can be a liability. Because when you superheat a very small area of the joint, what can happen is the components of that joint, like your boiler bushings or whatever you're silver soldering, will actually melt before the joint itself gets hot enough to properly flow the silver solder. I know that might seem unintuitive, but trust me, I have done it. I ruined a lot of boiler bushings when I was starting out because I started out trying to use oxyacetylene because the big kids on YouTube use it, and so it must be the best, and it made me feel big and important. You don't need oxyacetylene for this. Propane is great, it gets plenty hot enough, and it's a whole lot cheaper than acetylene and oxygen are, and you want a big flame. I know, again, that seems counterintuitive, but you want to heat up the entire assembly. Just like in plumbing soldering or electrical soldering, the secret to success is that the metal itself must melt the solder, not your heat source. The heat source is there to get the base metal hot enough to melt the solder itself. That's also why you want the big flame, because if you've got a large mass of, let's say, copper in a boiler, that metal is all acting as a heat sink. It's sucking heat away from your joint and keeping you from getting it hot enough, fast enough. Remember when I talked about flux spoiling? That's the challenge. You have to get that joint interface hot enough, fast enough before the flux spoils. And the metal, the massive metal that you're heating up in the whole assembly is working against you. It's sinking that heat away from the joint, trying to keep you from making that a good joint. Now, I will say there's one special case where acetylene for silver soldering big boilers is useful, and that's for stay bolts. I'll put a link in the description to a great video by an Australian model engineer demonstrating a technique for using a big propane torch to heat up the entire assembly, and then using a second person on an acetylene torch for microheating the area around a stay bolt. But again, the key takeaway is that the propane torch is doing most of the work. The acetylene torch is acting like a scalpel to close the deal, as it were, but the propane is really the key to the operation. Apologies to my regular viewers who've heard versions of this speech a dozen times, but people still keep commenting that why don't I use acetylene? Hopefully that clears it up one more time. One more technique I'll recommend from Kozo is the stainless steel scratch rod, just a simple piece of round bar with a point ground on the end of it. This allows you to wrangle your solder while the flux is melting, and also once the solder has flowed, you can push it around with this and make sure that it gets into all the parts of the joint and really makes nice fillets. You will also need a hearth. As you see here, I've got a bunch of fire bricks stacked in a little platform. Something very basic like this is all you need. These fire bricks are the ones that they sell at hardware stores for lining wood stoves. Don't use regular bricks or anything else. Fire brick is a special substance that's very, very dry. It won't explode under heat because there's no moisture in it, and it will reflect the heat back and make a very nice environment for silver soldering. You can also build little caves out of it if you're doing larger assemblies. It helps contain the heat, and then of course also acts as a backsplash so you don't hypothetically melt the insulation on your garage door. Hypothetically, I don't know why someone would ever do that, but I suppose it might have happened to someone. Definitely not me though. I mean, I'm not that stupid. I would never melt the insulation on my garage door. Oh, is it hot in here? Oh, there's my phone. I'll be right back. All right, pickling is done, so I gave those parts a quick rinse to get the worst of the acid off, and let's get some flux in there. You want to cover all of the mating surfaces with flux. Everywhere those parts touch needs to have flux on it. When in doubt, use more. You really can't use too much flux. It's a persistent myth that the solder follows the flux. It doesn't. The flux controls where the solder can and can't go, but the solder actually follows the heat. So using more flux is never a bad thing, and it will help ensure success on your joints. Using too little is fatal. Using too much, there's no downside. Don't forget to flux those screws as well. We want solder to flow all the way down through those screw threads, and it can't do that unless there's flux in there. So cover the screws in flux, make sure there's flux under the screw heads and down the threads and in the screw holes, everywhere. Next, you got to plan how you're going to apply the heat to the joint. You always want to heat the joint from the far side of where the solder is sitting, because that guarantees that the solder is not going to melt because the torch flame is hitting it. It's going to melt because the metal is hot enough to melt it. And that is how you guarantee a good joint. That is 99% of the secret of silver soldering, is making sure that it's the metal melting the solder. So that's why I have it sitting up on these little pieces of fire brick. If your solder is not flowing into the joint, but it's like pooling and balling on the surface, that's the problem, is that the silver solder has melted from the torch and not the metal. And now let's get the solder in there. I like to use the Kozo technique of cutting pieces of solder and laying them in the joint ahead of time, rather than applying the solder after the joint is hot. The advantage of this method is that it guarantees that the solder flows as soon as it can, and no sooner and no later, because the solder is already sitting there. So as soon as it hits the temperature, it's going to melt. You don't have to guess when the joint is hot enough and try to touch the solder in there at just the right moment. In this example, both of my components are roughly equal mass, but if there's a big difference in mass, then apply most of your heat to the larger part. If the back of the joint is not accessible, sometimes it isn't, like on boilers, then heat around the joint and try to keep the flame from touching the solder. All right, let's get the torch in there and start heating. The next thing you got to learn is how to read the flux. The flux goes through stages, and it tells you what's happening with the joint. The first thing that happens is all the water boils off. you'll see lots of bubbling, and the flux will turn into a dry powder that's kind of stuck to all the surfaces. The next thing that happens is the flux starts to foam up. That powder is melting and reacting. It's cleaning the surface, and that creates a bunch of off-gassing, which makes this white foam, or black foam if you're using the black flux. Now you'll find out why fixturing is so important, because the boiling of the water and now the foaming of the flux is going to make everything move around, not to mention the wind from the torch. But your solder is going to want to wander off. That's where the scratch rod really comes in handy, and those parts will absolutely have moved by now and ruined your joint if they weren't screwed together like this. The next stage happens quickly. That foam melts away, the flux turns into a very clear watery liquid, and then almost instantly that solder is going to melt and flow into the joint. This is your moment to push the solder around with the scratch rod if you want to ensure a good fillet, ensure it gets into all the places. Also a good idea to wash the heat around the whole assembly. Make sure all of the parts of the joint get lots of heat. Again, because the solder chases the heat, it follows the heat. Once the solder looks like it's flowed nicely everywhere, then stop. No need to go too far. And the important takeaway here is that this entire heating took less than a minute. You need that solder to flow within 5 minutes, or the flux will spoil. If it takes longer than that, you can use the black flux to squeeze a little more time out, but you probably need a bigger torch. Then once the part has cooled to where the solder is visibly no longer liquid, I like to move it over to a cold surface like my metal bench top to help it cool down. Don't dunk the part in water or anything like that. You don't want to shock it. You want it to cool down naturally, but we want it to go back into the pickling acid while it's hot, but not too hot, so it needs to cool down some. How do we know when the temperature is right? Here's a little trick. You can dribble some water on the part with the end of your finger. If you get Leidenfrost effect, where the water turns into spheres and rolls off the side as if they were ball bearings, that's too hot. Once the water droplets land on the surface, disperse, and then vaporize, the temperature is just right. You want it to go into the flux while it's hot because that makes the cleaning action of the flux much more effective, but you don't want it to be so hot that you're going to flash boil your pickling acid, which is going to create dangerous vapors and cost you a bunch of acid and generally create a mess. Another 5 minutes and we can take it out again. This post pickle cleans off all of the flux, residue, and soot from the torch and so on, and makes the part nice and clean again. It's not going to look clean, but hang on, we'll get there. After taking it out of the pickling acid, the soot will all be loose, especially if you put it in nice and hot. So a little bit of scrubbing with a toothbrush and that'll all come right off, all of that residue and soot and everything, and the part will look like this. Time to inspect it. We want to see a nice thin layer of solder between the parts, like we have there. If the joint was too tight, you won't get that. And we should see a nice fillet along the sides. And this is a bit of a heavy fillet. It can be smaller than this. This is because I used the 56 and also because of how much solder I used. I tend to use too much. But we've got a nice fillet and a nice layer all the way around. There's some leftover flux residue on here. We'll clean that off to make sure we can inspect the solder all the way around. That all looks really good. Now you also want to check your fixturing screws. You really want to see this solder coming through all the way around the screw heads because that means solder flowed all the way up into those threads. This other screw is a little suspect. If this was a really critical joint like on a boiler, I would probably go touch that up. For something less critical, like a basic assembly for something mechanical, I'm sure it's fine. But if you do want to touch it up, now's the time. The part is still pickled, it's still clean. You can put it right back on the hearth, flux it, heat it up again, get some solder on there, and improve that joint. But assuming we're happy with it now, the other thing you'll notice is that everything's got this kind of pink staining on it, which is alarming for the beginner. You might think, oh, I've ruined my part. This is actually the copper precipitating out of the brass alloy under the extreme heat of the torch. That might sound like it's weakening the metal, but it really isn't. We're talking about like 1 atom thick of copper here, and it rubs right off with a little bit of red Scotch-Brite. A few seconds and it's looking like factory fresh brass once again. So don't panic about the appearance. Don't worry about the strength of the material. It's fine. Now the fixturing screws, on the other hand, we do want to get rid of. Odds are you don't want screw heads sticking down on the bottom of your part. A few strokes with a coarse file and then finishing up with a fine file makes short work of those. If your silver solder has flowed nicely through the threads, then those screws will completely disappear and you'll never know they were ever there. If I freeze frame this at just the right angle so that the light is catching it just right, you can just make out the body of the screw and a very thin ring of silver solder around it. The other screw, where I didn't get quite as good a penetration, you can see a little bit of a dark line there where the edge of the screw is, but again, from a distance you'd never know. You can only see it when the light hits it just right. And again, as long as this isn't a boiler seam or something, that's no problem at all. If you get to this point and decide you still want to touch it up, you still can. Solder will flow down in there. Just put some more flux on it, heat it up again, and you can improve it. One last pro tip for part cleanup. You can buy these buckets of Scotch-Brite wheels for rotary tools on places like eBay. They're very cheap, but they actually work really well. The only downside to them is that they are extremely consumable. They clean up the parts really nicely and they save your fingers from working on these little corners and stuff, but you will go through a lot of them. So I only use them in places where I really need the part to be clean if it's going to be visible. Most of the time, cleaning the part up to this degree is not really worthwhile. But if you want it to look like jewelry, at this point you can get out the 1000 grit sandpaper and then go to the buffing wheel and so on. You can make it look as nice as you want. How you spend your time is up to you. To summarize the critical points here then, fixturing, joint clearance, pickling, proper fluxing, heat the far side of the joint, use your scratch rod, pickle afterwards once again, and you will have success in this process. The only times I've ever had silver soldering fail is when I got lazy on one of these steps. Silver soldering is all about the details. The details matter every single time. This video is essentially a compilation of techniques I've learned mostly from Kozo and his amazing article, The Art of Silver Soldering, which you will find in the back of the A3 Switcher book, or you can order it from Livesteam and Outdoor Railroading magazine. It's probably the best single piece of writing ever done on silver soldering, I think. His technique I find to be the most idiot-proof, the easiest to learn, and it's the bulk of what I've synthesized here in this video, but I've also thrown in some tips from my own experience and from boilermaking books and a few other sources. So hopefully this was useful to you. Thank you so much for watching. Thanks to my patrons for making all this content happen, and I'll see you next time.